Hello, everybody. This is Professor Ma, and this is the introductions on the sections on vector value functions. Vector value functions are parametric functions. To record a parametric equations, we have a parametric curve, so we have a point that's floating in space, a red dot, and I can track according to the times as the using time as the parameters, and I can track the positions x t, y t, z t, and this is called parametric equations, or they call the coordinate functions. And we say the curve is continuous if every one of the components is continuous. If I want to see these curves as vectors, as a point, as the endpoint of vectors, so then I change the notation slightly, so now I use this vector notation, or I use the IJK notations over here, which is convenient because it's one equation. I don't have to look at three different compartments, x, y, z. And when we treat these things as vectors value functions, basically we're trying to think of now the points as endpoints of vectors instead of positions. So we can do algebras with the geometries with the vectors. Vector value function as length, or it is the same as the distance to the origins for the parametric equations of the point. Same thing. And it is a function from time into length. So it's from real line to real, from real to real. And here are examples of vector value functions or parametric equation we had before. One of them is the equations of the line passing through in the direction 2, 3, 4, going through the origin. The other one is, next one is shift that line to the position 1, 4, 5. You can think of that now as a point of origins. And then we will get these sets of parametric equations. Here is an interesting parametric equations in 3 space. The y equal to 2. Z means everything's taking place on the plane y is equal to 2. This is x, y, and the other two components, x and z's, are circles. So therefore, basically, you're looking at the track of a circle circling around on the screen that's 2 feet in the y distance, 2 units from the y distance. Now we're going to move it. Suppose instead of at y equal to 2, we're going to let y change with time. So in other words, as time goes on, the screen moves out, moves outward. But the point is doing the same thing. It's still circling around on that particular screen. So y equal to t. And since the screen is moving continuously, so the point actually travels through the space, and as it travels through the space, it spirals on the cylinder with radius 1. And notice if I were to say do something like this, multiply everybody by t, except the x and z component. And what we'll do is that instead of circling of radius 1 tracks, now have radius t. Radius equal to t. And meaning that the points actually is spiraling out with a bigger and bigger radius. So I can do things like that to create all these interesting spirals. And in particular, this one is along the y-axis because that component's x-axis acts like the time component. We can define limits, and this is where the vector value notations calc. We think of these as vectors, and then we think of these as vector subtractions. So ct at time t, the vectors is here at time t plus h, and the points over here. And the subtractions is these displacement vectors. Exactly. What's the position changed? Is a position change vectors, the directions in the units. And we let h go to 0, what's the effect of that? Well, in other words, when h go to 0, then this position change vector is going to change as I shift along, as I move along the red line, and then I divide it by h, and in the limit difference quotients, I will get a vector, first of all, that's tangent to the curve. And it has certain length, and that length indicates how fast the speed of the point as it travels along these curves. Hence, we say the tangent vector as a point is this C prime. It can be calculated very easily. We calculated component x prime and y prime, the z prime. But there's one thing you have to be a little careful. We only say the point time t is differentiable, or it has a tangent vectors for vector value functions only when the tangent vector is not 0, because the 0 tangent vector has no direction, so it cannot act as a geometry, as a tangent vectors. And this is quite different from when we have one variable y f of x, f prime s equals 0 means the derivative at that point is 0. Okay, f of prime of a, and that makes perfect sense. I can talk about derivative equal to 0, but having vector value derivative equal to 0 vector, that makes no sense. Hence, we will say a curve, parametric curve is differentiable, provided tangent exists, C prime exists, and not 0. Okay, this is a crucial difference between the vector value functions and regular one XYZ functions. Here's an example that shows actually the trajectory, the path of the point. One of the questions we are interested in always is, okay, and here's the parametric equation based on t, but exactly what's the path it took? In other words, I need x and y equations. I want to eliminate the t out of the pictures. In general, here's how we do it. We solve for t, which is a difficult thing to do in general. It's a complicated equation. Then if you can solve it, then I can replace the t in the other equation by the x. That I don't have t anymore, I only have x and y related. And this is the way we find the xy equations or the graph for the path. And here is the graph for the path. It's basically y is equal to x to the 3 half power. And at t equal to 1, that's the location 1, 1, and that is tangent. We calculate the derivatives. T squared, t prime is, t squared prime is t 2t, and this is 3t squared. So that's this derivative, and we plug in the number at time t equal to 1. Now I get the tangent vector. And the speed is square root of 13 at t equal to 1. We can define accelerations, second derivatives, and we can define the speed, the velocity, the norm, the appropriate absolute value or the norm of the C prime and the C double prime, the accelerations. And here is examples. Calculate the tangent, take the derivative once, calculate the acceleration, take the derivative again. In front of I is 1, and derivative of 1 is 0. So C double prime of t, there's no I component. And, and that's the length of the tangent and the length of the accelerations. And notice in this case, if I dot C prime and C double prime is 0. And what does this say? This says, oh, in this case, the acceleration is perpendicular to the tangent. What's the relevancy of that? Well, this, remember, this is very similar to the other example we have with the t in the y component. This one is in the t in x component. In other words, if this is another is a spiral things again. And let me put these spirals in this way. Up and down. Oops. Okay. That's kind of. Man, this is the central axle of the spiral, if you like. And what this is saying is the tangent, of course, is the directions along the edge you're heading up, the tangent line, okay, at any given point. And as we go up, of course, the tangent change. So the change in the tangent, that is the second derivative, is perpendicular towards. In other words, as the acceleration is perpendicular towards, and so it's pointing inward because you're accelerating, you must be turning in the acceleration, and this is the 90 degree. In which direction is this going on? Oh, this is exactly the same direction. If you ever go up a staircase, the individual steps as it goes up, and it's the central pole, the individual step is perpendicular to the pole in the middle. That's the directions of the accelerations as we continue up this spiral. Okay, so that's just an observations of these examples. And what are the rules for derivatives? The sum and difference rule, I can prove the constants, all these are all the same as before. And the product rules, it's exactly the same as before, but there are 3 different products. And there's a scalar product. Okay, ft is a function in time, so I can multiply that to ct is like x, y, z here. Of course, when I multiply this as I multiply f times each component. So there is this product, and that's a dot product, and that is cross product in 3 dimensions. So the last one is only for c and d in 3-dimensional space. And if I take the derivatives of those products, they follow exactly like the product rule before. And so here's an example of the calculations of starting. This is an example of crossing 2 lines and trying to find the derivative of that. And finally, and one of the very important theorems concerning all of this is that if I have a curve or vector value function where the length of the vector is always the same. You see, what do you mean length vector is always the same? It means you're traveling in a circle. So in 2-dimensional space, and you have this circle of radius k. And if you see, it's always length k. Means your curve is going along a circle, but maybe it goes back as time changes. But it always, it's somebody jogging around this circular track, back and forth. In three-dimensional space, it means the particular curve is on the surface of the sphere. You can think of basically a car or ant that's crawling around on the sphere, the path, because the distance to the center is always the same. And then the theorem says if that's a track, if that's a curve you have, then the tangent of that curve at every point, that tangent is always perpendicular to the vectors to that point, like this. In three dimensions, these will be the vectors starting from the origin, go to the surface of the sphere, and then your tangent to the curve will be perpendicular. Then how do we prove that? It's very simple. You basically take the derivatives using the dot product, and then you wind up the curve C, the vector value function C of t dot with its derivative 0. Which means what? Which means the vector, the point C is over here. I mean, the curve C is here, and here's the origins, and you connect dots to that path, and as the curve goes along on the sphere surface, the tangent, the direction it goes, is always perpendicular. It doesn't matter which way it heads. That heading is perpendicular to the point on the curve. Yeah, that's it. Okay. These we will use later. Oh, that's not it. These we'll use come back to later to justify things being perpendicular again, the dot product. And then we have integral, which these are really self-explanatory, and I'll let you read about these. That's it. Have a good day, and see you later. Bye-bye.